There we go.
Right, okay. So I'm using my camera to record this, so I do apologise if it's a bit funny. But anyway, yeah, up until now, from the day you were born to this moment, we've dealt with coordinates in 2 dimensions. And those coordinates have been described using an XY pair. And we've described lines on those graphs using equations, not exclusively that look like that, but which follow that sort of form, where the relationship between the y value and the x value is explained in some way. So, to get to this value, you do something to that value. So, you multiply it by something and you add something. And that's all very well until we want to work with 3 dimensions. So until we want to join NASA and predict whether we're going to be hit by asteroids or did you? I think Elon Musk is an absolute plonker. But did you see that rocket getting curved?
Yeah, it's pretty cool.
Flipping heck! Goodness me! And all the everyone cheering, all that. Oh, this is brilliant. Anyway, sorry. Yeah. Yeah. If we want to do anything in 3 dimensions, we need a way of describing 3-dimensional space. So here's what we do. You've got to imagine that axis gets flattened. All right. So we've got it looking like that. And then we have a third axis that comes up, which we refer to as our z-axis. And so, it's good, isn't it? What do you think of that, Jack? So what we now have, when we have a 3D coordinate, is we have an x direction, a y direction, and then a z direction. So it won't come out on the camera, I'm sorry, but if you imagine this is the origin here, so that's the y-axis, and that's the x-axis, and this is the z-axis coming up here. That's right. Yes. Now it's really hard to draw 3D coordinates accurately, so I'll be absolutely frank with you. I don't bother. Okay. You'll see when we get to some questions what I mean by that, but I don't bother. And when we want to describe lines on a 3D grid, we need an equation which describes not the relationship between x and y, but between x, y, and z, which is more complicated, isn't it? Which is more complicated. These ways of describing lines on a grid by talking about the relationship between the 2 values, or 3 values, are described, are referred to as Cartesian equations for lines. Cartesian is a word that comes from the guy that thought it up, and that was Descartes. So Descartes was the first person to sort of describe lines in this way. So a Cartesian equation describes the relationship between, in 2 dimensions, these 2 numbers, and in 3 dimensions, these 3 numbers. But we don't often talk about 3D space in terms of coordinates because we're nearly always talking about motion and movement. So what we very often talk about when we're dealing with 3D space is vectors. Okay? So we're used to vectors in 2 dimensions already, and we're used to the idea that when you have a vector like 3, 4, that's a journey where you go along 3 and up 4, which is a 2-dimensional journey. So, that. And you remember we tended to use bold little letters to describe vectors, so we'd say A is 3, 4. And any sort of journey that's along 3 and up 4 is the same description, And so, we can now have vectors in 3 dimensions which have 3 numbers. So this vector here is along 5, out 4, and up 3. So it's something like that. So it's a journey looking like that. And it could be that we just describe a journey like this, but when we're dealing with 3D coordinates, what we tend to talk about is a position vector, which says actually, this is how you get, it's not just any old journey of along 5, 4 and 3. It's how you get to a point out here from the origin. And so do you remember the other notation we used for vectors was that using capital letters, where you're starting and where you're finishing. So that's my vector OA, and of course the direction is important, isn't it? The direction is important. So we've got two sorts of vectors. You've got a vector that describes a journey, which can be in 3 dimensions. So, you know, we can have a 3-dimensional journey, which, I don't know, a long 4 up, 7 up 1 would be something like that. And any journey in 3-dimensional space that followed that would be the same. But these position vectors are anchored. They're actually saying this is how we get from here to here. Okay. So let's start with a little problem. Let's say I've got 2 3D vectors. Okay. One is to get to a point A. Let's say that is. And another is to get to a point B. Let's throw in a negative number. And I want to know how I get from A to B. All right? So here's when I say I don't really worry about what they actually would look like in real life. What I would do in that question is I'd say, okay, here's a couple of points, A, B, in 3-dimensional space. There's the origin. There's OA. There's OB. OA is 4, 5, 3. OB is -3, 4, 8. I haven't in any way tried to make those accurate. My question is, how can I get from A to B? Now, obviously I don't know how to get from A to B along that road, but there are some roads that I can use to get from A to B. Go on, see if you can puzzle that one out. I guess, yeah, I should in the beginning. This is just a vector which isn't fixed in space. This is a position vector which is fixed in space and specifically is anchored at the origin. These two are 2 position vectors, therefore. AB will be a position vector, which is how we get from A to B. What do you reckon, Thurston? Any suggestion?
Would it be just negative A plus B?
So go on, give me some numbers.
Negative 7, negative 1, 5.
Yeah. To get from A to B, you go backwards along backwards along OA, so it would be -4, -5, -3, and then forwards along there. So -4 -3 is -7, -5 plus 4 is -1, and -3 plus 8 is 5. And you'll find you get better at doing this, because actually all we're doing is we're asking what's the difference, isn't there, between these 3 pairs of numbers. So from 4 to -3 is a drop of 7, from 5 to 4 is a drop of 1, and from 3 to 8 is a drop of is an increase of 5. And so that's that vector there. We could go further and say, right, how long is the journey AB? And I'm hoping at this point you are remembering about me selling the sticks in boxes. Do you remember the sticks in boxes? Because the journey at -7, -1, 5, if I go back to my original axes here, that's a journey of, I'm regretting using -7, -1, 5, but there we go, we'll stick with it. I'll have to start again, won't I? So my x-axis needs to sort of, going to be like that, isn't it? So we've got, so I need to go to -7 up there, and then I need to come out -1 to here, and then I need to go up 5 to there. So we're happy that that's a box. It's the worst diagram I've ever drawn. Are we happy that that's a box where the dimensions are 7, 1 and 5, and the distance is the internal diagonal? Yeah. Don't worry if you can't see it. The basic answer is the length of a 3D vector is just that number squared plus that number squared plus that number squared square rooted. Do you remember that was the shortcut for working out the internal diagonal of the box? So that was and that's a bad example actually because it doesn't. That one doesn't start from the origin. That's just a journey. But yeah, anyway, it's the internal diagonal of a box that you get. Now, if I was king, that would be the way that vectors were described. Okay, we only describe vectors using columns. All right. I am not king, sadly. I was up in the loft last night looking. I found a letter I wrote to the Queen when I was 7, telling her how much I'd enjoyed Trooping the Colour, and she replied. She gave me she didn't reply. One of her flunkies replied. But I've got a letter with Buckingham Palace. I was a weird kid. Right. Okay. Now, if I was king, then that would be it. We would describe vectors in that way. But like I said, I'm not king. That was the closest I ever came to royalty. What is sometimes used, and I'll tell you in a minute why it is used, to describe 3D vectors, is they use 3 special vectors. They describe a vector that goes 1 in the x direction and nothing in the y and the z direction, and they call that I. So I is like a vector that goes 1 unit in the x direction, and there's a similar vector that goes 1 unit in the y direction, but no units in the x and the z direction. And there's a similar vector that goes no units in the x and y direction and 1 unit in the z direction, which is called K. And so this vector here, that was 4, 5, 3, could be written as 4 lots of I followed by 5 lots of J followed by 3 lots of K. Now, can anyone willing to give a punt at why the I, J, K notation is used rather than just using the columns?
Make a bigger matrix.
It's not that. Which is it?
Also, be more annoying.
Well, no, it's about word processing. It's much easier to type that in Word than it is to type that, isn't it? So it's sort of a bit of laziness, really, on the part of mathematicians. If you want to, represent your work on vectors, it's much easier to be able to type it. And so the IJK notation just makes it a bit more writable. But I have to tell you, whenever I see a question with IJK notation, I rewrite it as a column vector. Now, I know I can do this because you're all such superstars. But you know, normally this would be done over several lessons. So I'm sorry that we're sort of going bang, 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 bang. But we've introduced the idea of three-dimensional coordinates, which we've straight away stopped using and gone into three-dimensional vectors. And we've introduced a second way of writing three-dimensional vectors using I, J, and K notation, where I is a vector of 1 unit in the x direction, J is a vector of 1 unit in the y direction, and K is a vector of 1 unit in the z direction. Why am I doing all this? Well, we want to describe lines in 3 dimensions. This is where we're going, and we don't want. Well, we do have to use Cartesian versions, but that Cartesian version, some x's equal some y's equal some z's, it's just really, really confusing. So what we use is a vector method of describing. So that's really what I want to do today, the vector equation of a 3D line. The vector equation of a 3D line. Here is a line drawn in 3 dimensions. Okay? I want to describe this line so I can work out if it crosses other lines. You know, it might be the path of an asteroid, or it might be the path of a rocket, and I might want to know where that asteroid or where that rocket are heading. Let's go back to Cartesian descriptions of 2-dimensional lines. In its essence, this line, when I teach this to students lower down the school, I say you start here on the y-axis, and then that's the gradient, that's the direction. So basically you're describing a line with a point and a direction, a gradient. And and when we were solving those, what's the equation of this straight line things at GCSE, I always made you write gradient, point, didn't I? And that's the way we did it. We do the same when we want to describe a line in 3 dimensions. We say, okay, if I want to describe this line, let's pick a point. There we go. Pick a point. And let's work out how I can get from the origin to that point. Okay? So let's work out how I can jump on the line. All right? So I've jumped on that line. Let's say that vector is 4, 3, there you go. Okay, I've jumped on the line. I'm on the line now, but I want to now sail onwards with the line. So what I now need is some idea about what direction that vector is going. And that direction isn't a position vector, it's not fixed in space, it's one of the original vectors that can just be any journey. So let's say in this case, that vector is trying to make it vaguely, so 1, 7, minus 1. Okay? So I know that anywhere on that red line I can get to by jumping on and then doing some multiple of that direction. So if I want to get here, I jump on and do 2 lots of 1, 7, minus 1. And if I want to get here, I jump on and do minus 1 lots of 1, 7, minus 1. So what we do is we write it like there, where lambda, which is a Greek letter, apologies if I'm patronising, we've used it before, is just a multiple. It's not a vector, it's a scalar. So the vector equation of this line, and we tend to call lines with vector equations R, is equal to some jumping on point and a multiple of some direction. That's the vector equation of a line. Some jumping on point, so how do you get onto the line from the origin? And then what's the direction? And of course that direction could be written in a number of ways. So it could be the same line can be described by 4, 3, 5 plus lambda 2, 14 minus 2. Or it could be described as 4, 3, 5 plus lambda minus 3 minus 21 plus 3. That would be the same description, wouldn't it? So the vector equation of a 3D line is not that form, it's this form, r equals some point plus a multiple of some direction. And in the textbook, finally getting to the syllabus, you can see that on page 168, where they say, is that not working? Why is that not working? Oh, pen and paper. So we tend to refer to the point as A and the direction as B. And varying this will give you different points along the line. Okay? So the vector equation of a straight line, and you can do this in 2 dimensions. It's just, you know, that's a 2-dimensional vector, that's a 2-dimensional vector. And in fact, at year, if you did AS normal maths, then you would only be in 2 dimensions. A level maths does 3 dimensions, and AS further maths does 3 dimensions. So that's why we're jumping straight to 3 dimensions. So you've got to look surprised in year 13 when you first look at 3 vectors, okay? You've got to look surprised. So example 1 is a non-question, because if I want to find the vector equation of a straight line that passes through the point A with position vector, remember, is how you get to a place from the origin, and is parallel to that vector, so that's a direction vector, then we're just going to say, right, it's 3 minus 5, 4, plus lambda. Now there's no j here, so that's 7, 0, minus 3. Now, people always say, do I need to write it in IJK notation? I guess if the question is in IJK notation, we ought to, so it would be 3i minus 5j plus lambda 7i minus 3k. So I mean, that's an embarrassingly easy question. I'm not going to ask you to do that one. But I think it is worth doing this one. So the first thing is, think of that as a vector with position that. Remember what you need. You need a point, well, we've got a choice of 2, and you need a direction. If only we knew a way of working out, if that's A and that's B, how to get from A to B. Okay, go on, have a go. Have a go, see if you can do it. notes again how I made no attempt to get those points in any way accurate. So point, I could use either, doesn't matter which one. And then direction, Rory, what do you reckon for the direction? So that's...
I put 2, 1, 2, 3.
You are absolutely spot on, yeah. This is the line. It goes through these 2 points. So to describe it in this way, we need a point, so I could have used that one or that one. Either of those could have gone there. And a direction. Well, the direction of the line is this vector here, and that's what we already worked out. And so that is the answer. Now, shall we try and draw that on our calculators? Because that's very exciting. So, now, I genuinely have practiced this, but that doesn't mean it's going to work properly for me this time. So I'm going to go to 3D graph. And I'm going to delete the lines that I've already got in there. So the first thing I'm going to do is press type, and I want to draw a line. So yeah, the line is okay. So I'm going to type XE. And I want it to be not the Cartesian description of line, but the vector description of line. Here is a Cartesian sort of template, something to do with x equals something to do with y, something to do with z. Don't want to use that. So instead, we're going to use the vector description. So I'm going to press vector, and straight away it's given me a template that looks like this. Obviously, they use a different letter to us, so lambda t, it's the same thing. So if we type in our point, and direction, I think you have to press XE at the end. Yes, you do. Right, okay. Now, we're going to try and draw it. Of course, it depends on how your axes are scaled. So let's press draw. And no? Now, if you've got nothing, it probably means your axes need to be scaled. Now, do your axes all look like that?
Not quite.
Mine's 3 by 3.
Mine's 10 by 3.
Yeah, no, I mean in terms of the orientation of the box.
Yeah.
Yeah.
So that's, yeah, I don't particularly like that, but yeah, so we've got X and Y this way around, Z correct. So yeah, if you want to change the scale, it's V window, so that's F3, and you don't touch the grid or anything else, just touch the X min and max, the Y min and max, and then scroll down Z min and max. Don't touch any of those things, because it will. So if you go from -10 to 10, you can see that line. Don't touch the grid, don't touch anything else, just the X min, X max, Y min, Y max, and then Z min, Z max, which is off the page. You have to scroll down. And then when you go X in, you have to, oh, I thought you had to read it. Now, what you should be able to do is plus and minus will zoom in, but then I think you can then rotate it. Yeah, so the cursor buttons will rotate it. So can I rotate it so it looks, that's better. Yeah, there you go. So I can rotate it so it looks like I want it to look with X and Y and Z.
Oh,
And
It's not as big as that.
it does take it a while, doesn't it? You know, it takes it a while.
Did
It's,
you do the how
okay, right. So let's have a go at.
Why is it
Now, what that means, describing a vector equation like that, is that R is anywhere on the line. So R itself is a vector. So any point on the line can be obtained by fiddling around with this value. So in my example here, if I made lambda equal to 2, I'd get 4 plus 2 times 2, so that's 8. 5 and minus 4, which is 1, and minus 1 plus 6, which is 5. So 8, 1, 5 is a point on the line. So is 4 minus 6 minus 2, 5 plus 6, that's 11, and minus 1 minus 9, so is that. So varying, mucking about with. And of course that vector there could be described using a 3D coordinate. So this is a sort of a, we'll have a go. Given that the point A, B, 0 lies on the line, find the value of A and the value of B. You know what I'm going to do straight away? B17? Two and a half times 6 is 15. So 2 plus 3. Does that make sense?
Yeah.
So I worked out what the multiplier was that would get me to this point, so it had to be minus 2.5. And yeah, I should have made that point. Yeah, this doesn't have to be an integer, it can be any value at all. And then sort of work backwards. Right, very quickly. We've done it. One more question and we've done it. On page 173, question 3. So remember, find the vector equation of a line, so we need a point and a direction. Any suggestions for direction? Go for it first.
001.
Or 002, or 003, or 004. All of those would be directions which are parallel to the Z-axis, that's right, yes. Yeah. 3 questions there I suggest you have a go at. I've done, that's a sort of crazy speed, and I hope you sort of managed to get your head around it, but yeah, you'll get used to it. You'll get used to it. And vector equations are really nice and easy in 3D. Sadly, we do need to be able to convert a line, the vector equation of a line, to its Cartesian equivalent. And Cartesian lines in 3D are not so much fun. But goodness me, you're all superstars. You're all had no trouble whatsoever. And my phone didn't fall off. So.